In today's lecture, we will talk about interference and system capacity. We will see that interference is a prime concern and has to be taken into consideration while designing cellular communication systems. The outline of today's lecture is as follows. We will first begin with summarizing what we have already learnt. Then we will talk about two important kinds of interference, namely the co-channel interference and the adjacent channel interference. We will then learn how to calculate the signal to interference ratio, which will have an impact on the number of users you can actually support. Finally, we will look at some examples. First, let us recapitulate. We learnt last time that the cell capacity and the reuse factor are interlinked. In fact, if you look at the cluster size n, as n decreases, the capacity of the system increases. Last time we also learnt about traffic theory. We looked at the Erlang-B formula, which tells us how to calculate the probability of an arriving call being blocked. The Erlang-C formula, which tells us how to calculate the probability of an arriving call being delayed beyond a certain time. We then looked at channel assignment strategies. There was a fixed channel assignment strategy and a dynamic. Finally, we looked at handoff strategies, which fell into the categories of hard handoff and soft handoff. Today, we will focus on the other aspect, which is interference, how to calculate it, what effect does interference have on the designing of cellular wireless communication systems. Interference is a major limiting factor in the performance of cellular radio. It limits capacity and increases the number of dropped calls. We will see that interference has a direct correlation with the quality of service. These are the various sources of interference. It could be another mobile in the same cell. It could be a call in progress in a neighboring cell, and there could be other base stations operating in the same frequency band. All of these can cause interference. Interference is more severe in the urban areas due to greater RF radio frequency noise floor and more number of mobile stations and base stations. However, life is not all that bad. Urban environment has an advantage. The path loss exponent, that is how fast the signal strength decays as you move away from the transmitter, is a bigger number. N, the path loss exponent, is usually close to 4 in urban areas, which will lead to a decreased interference level. So, there are both pros and cons for interference calculations within urban environments. Let us now look at the effects of interference. What does it actually cause? Interference can occur both in voice channels and the control channels. It does not discriminate. Interference on voice channels can cause crosstalks and noise in the background. On the other hand, interference on control channels causes error in digital signaling, which in then turn causes either missed calls or blocked calls or even dropped calls. So, you can see that interference will cause a decrease in the quality of service, both either in the voice channels, which are perceptible, as well as control channels, which can lead to problematic issues like blocked calls. Clearly, we have to do something about controlling interference. Now, let us look at two major types of interferences. The first is the co-channel interference known as CCI, and the second one is the adjacent channel interference or ACI. Co-channel interference is caused due to the cells that reuse the same frequency set. We have talked about this earlier. These cells using the same frequency set are called co-channel cells. On the other hand, adjacent channel interference is caused due to the signals that are adjacent in the frequency band. Let's look at an example of how co-channel interference occurs. First, let us look at a small cell with its own base station, which is located at the center. For the sake of simplicity, we have taken a hexagonal cell. We all know that in real life, cells are irregular in shape. Now, since the frequency band is being reused, there would be several co-channel cells. Let's put a mobile station first inside the cell. It is located at a certain position and is free to move around within the cell. The first co-channel cell is clearly located at a distance from the original cell, and there are not just one co-channel cells, but there should be several co-channel cells of radius r. So, let us put the second cell, the third, the fourth, the fifth and the sixth. Because of the hexagonal structure, there will be 6 co-channel cells in the first tier. Clearly, the location of the mobile will determine the exact distance of the mobile from the interfering base stations. Here, there are 6 distances from the 6 base stations radiating in the same frequency band. I have marked them as D1 through D6, and they are all different. These can be said to be co-channel base stations within the first tier. But please remember, the hexagonal cell pattern is being repeated throughout the area of interest. So, there will be a second tier as well. But clearly, as the distance increases, the interference levels would go down. So, the second tier would also contribute to some interference, though less. Unlike thermal noise, CCI cannot be overcome by increasing simply the carrier power of the transmitter. That is to say, if you are interested in improving S to I, the signal to interference ratio, we cannot simply pump up the signal strength and expect the signal to interference ratio to go up. This is because my signal is somebody else's interference. I cannot do that. So, we end up creating our own noise by increasing the signal strength. So, what is the solution? We have only one way to decrease the signal to interference problem, that is improve the S to I ratio, that is by physically locating the cells far apart. So, for similar sized cells, co-channel interference is independent of the transmitted power and depends on the cell radius r, the distance to the nearest co-channel cell D, and in fact the ratio D to R. To reduce CCI, the co-channel cells must be physically separated. That is, we have to sacrifice a value of n and maybe increase the value of n. Please note that today you can use signal processing techniques to further reduce the interference effects. There is an emerging technology called multiple input, multiple output systems, MIMO, which can also handle interference reduction issues. You can do coding to reduce interference as well. That is, you can use different kinds of codes in co-channel cells. Similar to what CDMA does, the interference of a co-channel cell may be rejected by your own cell. But if you do not want to carry out complicated signal processing techniques, you may as well increase the distance between co-channel cells. We know that the co-channel reuse ratio Q is given by D over R, where D represents the distance between co-channel base stations, whereas R is the cell radius. So, this is a normalized distance. Q determines the spatial separation relative to the coverage distance of the cell. For a hexagonal cell pattern, we have seen that Q is nothing but under root 3n. So, it grows as the square root of the cluster size. Thus, a smaller value of Q provides a larger capacity, but a higher co-channel interference. The question is, what is the trade-off? How much do we gain in terms of capacity and lose in terms of co-channel interference? We will look at certain examples to clarify the issue. So, we have to carefully understand and then design a system based on the trade-off between capacity and interference. So, the calculation of signal to interference ratio can be done as follows. The S to I ratio is given by the signal strength received at the mobile divided by all the power received from the interfering base stations. So, here on the numerator I have put the signal strength received from the desired base station, and in the denominator is a sum of various interferences from I is equal to 1 through m, where m could be the cells in the first tier, second tier, or even beyond. This is a general formula. The average received power at a distance can be written as PR, the received power, equal to the transmitted power P naught at a distance D naught, and D is the received power at a distance T. So, this is a normalized power, and N is the path loss exponent, which can vary from a factor of 2 to 4 depending upon the scenario. Please note that there is an inverse law, but it is not the inverse square law. It can be inverse cubed or inverse to the power 4. Let us now look at the various calculations based on the distance. If Di is the distance of the ith interferer, and we know that all the interfering base stations may not be equidistant, then the received power is proportional to Di raised to power minus n. N is the path loss exponent, which can range from 2 to 4. We can measure the value of n by carrying out the received power measurements with respect to distance. Thus, the signal to interference ratio for a mobile can be written as S over I equals R raised to power minus n. What is this? This is proportional to the received strength from the desired base station. R represents the cell radius, so you are actually putting your mobile station at the edge of the cell. In the denominator, I have a summation for I is equal to 1 through m di, where di represents the distance from the ith interferer, again raised to power minus n, the path loss exponent. Only for the first layer of equidistant interferer, we can put this equation as d over r raised to power n divided by m, just carry out the summation and assuming equidistant. So, d1 is equal to d2 is equal to d3, so and so forth till dm. So, you get an answer as under root 3n divided by m. This equation clearly gives a relationship between the signal to interference ratio and how it is related to n, which determines the capacity. So, as n increases, the capacity decreases, but the signal to interference improves. So, I can trade off the signal to interference, which determines the quality of service, versus the capacity of the overall system. For a hexagonal cluster of cells, let us look at one of the desired cell, with a base station marked as a red dot, and we put the mobile station this time close to the center of the cell. Then we put one of the interfering base station in the first tier, the second one, the third one, and so on and so forth till the sixth. Please note, irrespective of the reuse factor, irrespective of the cell cluster, in the first tier you have 6 interfering base stations. That is because of the hexagonal geometry. Here we have distances D1 through D6 to the mobile station. The cell radius is given by R, but since we have assumed that approximately all the 6 interfering base stations are equidistant because of the shear positioning of the mobile station closer to the center of the cell, I can put D1 equal to D2 up to D6, and so I equate it and I get 6 interfering station contributing to 1 by 6 d over r raised to power n, which is nothing but 1 over 6 under root 3n whole raised to power small n. Please note, the signal to interference is clearly independent of the cell radius. As long as all the cells are equally large, my R does not figure in. Okay. What figures in is capital N, the cluster size. Let us now look at an example from designing a system. What are our design parameters? Let us say the desired signal to interference is 15 dB. Based on some trials and tests, suppose the service provider says a signal to interference ratio of 15 dB is adequate. However, the service is being provided in a dense urban environment, say Connaught Place CP in New Delhi. Here, if you carry out measurements, you will find that n is close to 4. So, let us put n is equal to 4 for our calculations. What we would like to know is, based on these parameters, what is the required reuse factor. We are trying to link the signal to interference ratio requirements to the effect on the reuse factor capital N. So, let us try n is equal to 4. Remember, I cannot try any arbitrary value. N is given by I squared plus ij plus j squared, where I and j are non-negative integers. So, we know that for n is equal to 4, the d to r ratio is given by 3.46. So, by the simple formula of 1 by 6 under root 3n raised to power small n, we have 1 by 6 times 3.46 raised to power 4, which gives us 24, and in dB it translates to 13.8 dB. So, if you are using a reuse cluster size n is equal to 4, you end up having a signal to interference ratio of 13 dB. This is less than 15 dB. Yes, my interference values are much higher than my system can handle. So, we must move to the next higher reuse ratio. So, the next higher is not 5, it is not 6, the next higher n is equal to 7 is the next feasible ratio. So, we try n is equal to 7. So, these are the steps a system designer is doing while figuring out how to pick a correct value of n. For n is equal to 7, the d to r ratio is 4.58, which leads us to a s to I ratio of 73.5, when expressed in dB is nothing but 18.66 dB. What is our desired signal to interference ratio? It's 15 dB. So, I am in business, I am actually doing much better, it's more than 3 dB improvement in the required level. So, I would use a reuse factor of 1 by 7, my cluster size is 7. So, in an area like Connaught Place with dense urban buildings, I have a reuse factor n is equal to 7. Let us now change the example a little bit and look at a slightly different scenario. I would like to look at the South Delhi region, which is more suburban. It is not a concrete jungle. There are buildings, there are foliage, but not a very high density of concrete structures. Again, my desired signal to interference ratio is 15 dB, but the path loss exponent has gone down to n is equal to 3. Question again is, what is the required reuse factor? From our last example, n is equal to 7 worked. Let us see if we put n is equal to 7, what happens. The D to R is the same, 4.58. Using the formula calculated before, S to I comes out to be 16.04, which expressed in decibel is nothing but 12 decibels, below the 15 dB requirement. So, merely by changing the path loss exponent, I have been required to increase the value of n. So, we must go to the next higher reuse distance, which is 12. So, next try n is equal to 12. For n is equal to 12, the D to R ratio is given by 6, and signal to interference comes out to be 36. When expressed in decibel, it is 15.56, just a notch above what is required. But we are still in business because 15 dB is what is required. So, in suburban Delhi, I have to use a reuse factor of 12. Life is not all that bad, because here probably my capacity requirements are less, as opposed to the dense urban area where I have to support a larger number of people. So, it is following in trend. Higher concrete jungle density, we can handle more number of users, right. What will happen if we go down to n is equal to 2, which is truly our inverse square law, the free space propagation path loss exponent. So, we will look at another example to see what will happen if n is equal to 2. So, our design parameters this time are signal to interference again 15 dB, but it is a rural environment where we can hope to have close to 2. So, first let us put in perspective what we have already acquired in terms of n is equal to 4 and n is equal to 3. I have put here a graph. On the x axis is the cluster size, on the y axis is the signal to interference ratio in decibels. We are already familiar with the first curve, the topmost curve, which has been plotted for path loss exponent n is equal to 4. Please note that the points that have been marked are at discrete values 3, 7, 12, 13 and so on and so forth. What we have already seen is that for a 15 dB signal to interference ratio as desired, if we use n is equal to 4, the cluster size capital N is equal to 3 is not suitable. In fact, what is above this 15 dB is cluster size n is equal to 7, and the cluster size n is equal to 7 is recommended for path loss exponent 4. We also saw for the next level n is equal to 3, the path loss exponent n is equal to 3 forces us to go at a higher cluster size of 12. So, we saw in the last example that n is equal to 12 is suitable very clearly from this. If we move this green line up or down, we can simply find out what is the size of your cluster that you require to use. So, the next question is, what do we do for small n is equal to 2, the rural areas? Here, if we have to have the desired signal to interference ratio equal to 15, we search but we find that even if we go to a very high cluster size, we still do not reach 15. We have to do something else. We have to use some kind of a signal processing technique to do it, because if we go to cluster size beyond 12, you are really not using the power of reuse factor. Right? Cluster size normally are not typically larger than 12, okay, because we have to have enough number of customers in our service area. In the next slide, we would like to talk about the worst case calculation of signal to interference. When does the worst case interference occur? The worst case interference will occur when the mobile station is at the cell boundary. Why is it bad? Well, I am farthest from my own base station and maybe much closer to an interfering base station. This will lead to a poorer signal to interference ratio. Diagrammatically, let us put our desired base station here as a red dot, but this time I would like to place the mobile station at the very edge. It is possible. So, from the cluster of 6 co-channel cells in the first tier, 2 co-channel cells are clearly closest to the mobile station. The 2 interfering base stations are really much closer to the mobile station, for example, as compared to 2 others which would be at a farther distance. So, all 4 so far are co-channel cells, but the first 2 cells are much closer to the mobile station than these 2. So, approximately I can say that from the first 2 co-channel cells, the distance from the mobile to the interfering base station is roughly d minus r, where d is the distance between the base stations and r is the cell radius. On the other hand, the next 2 interfering base stations are at a distance approximately d from the mobile station. But that is not the end of the story. We have 2 more co-channel cells, but by the mere position of the mobile station, these 2 interfering base stations are almost at a distance d plus r. So, the 6 co-channel cells, the base stations there are differently placed with respect to the mobile stations. The distances are different, so the interference must be different. The approximate signal to interference ratio in this worst case analysis is given by S to I is equal to, in the numerator we have r raised to power minus n, again minus n represents the path loss exponent, r is the distance of the mobile station from its own base station. So, this numerator is proportional to the signal strength received by the mobile station. In the denominator, we have 3 factors. The first factor is 2 times d minus r raised to power minus n. This corresponds to 2 base stations whose distances are d minus r with respect to the mobile station. There are 2 of them, so I have put a factor of 2 here. Then there are 2 other co-channel cells whose base stations are located approximately d distance apart. So, 2 d raised to power minus n, and similarly for the farthest apart base stations which are at a distance d plus r. Now, if we represent the factor d over r as q, so take the r down into the denominator and you can write it as 1 over 2 q minus 1 raised to power minus n plus 2 times q raised to power minus n plus 2 times q plus 1 raised to power minus n. Please note that q typically is not a very large number with respect to 1, so we cannot neglect the 1 with respect to q. Fine. you will not have this -1 and +1 if you are doing the average case analysis, wherein the mobile station is located somewhere within the cell, not necessarily at the boundary. In that case, you will have 1/6 q raised to power minus n. So, there are two cases, the worst case and the average case. The worst case versus average case scenario can be seen in the current slide. Here in this graph, on the x axis I have plotted the cluster size, on the y axis I have the signal to interference ratio in dB. The first curve, the topmost curve, corresponds to a path loss exponent of n is equal to 4. The next one is n is equal to 3, and then the next one is n is equal to 2. What we want to see from this curve is how much does the worst case analysis differ with respect to the average interference calculations. So, the average is given by this continuous curve without the triangles, whereas the lower curve within n is equal to 4 is the worst case analysis. As expected, the curve for the worst case must be below the average case scenario, because on the y axis you have signal to interference ratio. So, the worst case interference is larger, so signal to interference ratio is lower. But question is how much? So, if you can see, for the case of n is equal to 4, the difference is large for small cluster size. Remember, small cluster size is what is actually used. Anything below this 12 is of importance. Cluster size larger than 12 is usually of academic interest. So, wherever our interest lies, yes, there is a difference between the average case and the worst case for n is equal to 4. Interestingly, when you have n is equal to 3, the difference reduces, and the trend continues when we look at the free path loss exponent n is equal to 2, the free space propagation, the difference is barely enough. That is, there is hardly any difference between the worst case and the average case scenario. In reality, n is equal to 4 would be used for a city like Delhi. So, let us now look at another design problem. Here we have to design a system for signal to interference ratio equal to 18 dB. We have made our requirements more stringent, about 3 dB more stringent than the 15 dB requirement in the previous example. So, the objective is as follows. We would like to know the cluster size for signal to interference ratio equal to 18 dB. We have, of course, the average case analysis and the worst case analysis. Now, for the average case analysis, the closest cluster size which goes above the 18 dB mark is n is equal to 7. Clearly, 18 dB requirement can be met in the average case scenario if the cluster size n is equal to 7. But please note that n is equal to 7 is not sufficient in the worst case scenario. It has dropped below this one. So, for the average case, even though n is equal to 7 suffices, for the worst case I must go to the next higher level, which is nothing but n is equal to 12. So, for the worst case I am bound to take n is equal to 12. Now, what will the service provider do? Either he has to think about all his customers who are at the edge of the cell, and the worst case analysis really applies to them. So, either he is nice and considers all those customers who are sitting on the fringe, and then for them and them alone he designs the cluster size equal to n is equal to 12, or he forgets about those people sitting on the cluster edge and just takes the average case scenario and puts n is equal to 7. What will he do? Well, if he has to make money, the ratio 7:12 is too much to lose out. He can support more than 1.5 times the number of customers if he goes from n is equal to 12 to n is equal to 7. So he will forget about those sitting on the edge of the cell and really do the calculation for the average case scenario. But please note that yes, these exact calculation of the average case and the worst case forces you to change the entire design. The effect will not be so prominent if I am working at n is equal to 3 and hardly makes a difference when n is equal to 2. So a service provider in Delhi must take this worst case situation into analysis, into consideration in Delhi, but not so much in smaller towns like Jaipur and Lucknow, and definitely not in the outskirts in the rural areas where n is equal to 2 is required. Now we look at the next type of interference, which is the adjacent channel interference. This results from signals that are adjacent in the frequency to the desired signal. This results from imperfect receiver filters that allow nearby frequencies to leak in. Please remember, your handset prices go down because the hardware put therein is cheaper, and the filters that we put in there also do not have too stringent requirements, that is, the sharp cutoffs do not exist. Clearly, if you have cheap filters, you will let in more adjacent channel interference. But we really cannot do much with the cost of the handsets, they must keep going down. So what is typically done is to use expensive, very well designed filters at the base station. In fact, the cost of the base station is being shared by so many number of users. So adjacent channel interference is actually handled more at the base stations, but also at the handset level also. The problem can be severe if the interferer is very close to the subscriber's receiver. So if my friend and I are going in the same car, and by whatever coincidence we both are assigned adjacent channels, then we will have crosstalk. Or if the interference is in a channel which is used for control, then one of the calls might get dropped or some other problems might occur. Another effect of adjacent channel interference is called the near-far effect. What is the near-far effect? When an interferer close to the base station radiates in the adjacent channel, while the subscriber is actually far away from the base station. Please remember, the path loss exponent is close to 4. The signal strength goes down very fast to the power of 4 of the distance. So if my interfering handset is close to the base station, whereas I am as a subscriber far away from the base station, my signal will get a lot of interference at the base station. Let us look at it from an example. Let us first put a base station and the subscriber. So subscriber is mobile and is located at a certain distance from the base station. But there are a lot of users, and let us have an interfering handset sitting inside a car which happens to be closer to the base station. And as luck or bad luck would have it, the interferer is radiating in an adjacent frequency band. So even though the subscriber is trying to communicate with the base station, by the time the signal reaches the base station, it is fairly weak. the path loss exponent is pretty high, and so what is being received at the base station is a low signal level, but still it can be handled, it is within the threshold. On the other hand, for the interferer, which happens to be located much closer to the base station, it is radiating in the adjacent band, and because of the imperfect filters, a lot of energy is leaking in, but a lot of high energy. In fact, in the next slide we will see what could be the relative strength of the interfering signals with respect to the desired signal. So, what should the base station do? It should invest in making much sharper band pass filters. That is where we have to work. So, the adjacent channel interference can be reduced by careful filtering, which means more expensive filters, and then of course attacking the problem at the root, which is careful channel assignment. The frequency separation between each channel in a cell should be made as large as possible. If a subscriber is at a distance d1 and the interferer is at a distance d2, then the interference value will be determined by d1 and d2, and the signal to interference ratio prior to filtering is given by S to I is equal to d1 over d2 raised to the power minus n. The same philosophy, the path loss exponent works inversely with respect to the distance. Let us look at an example, how good or bad the adjacent channel interference can be. Suppose the subscriber, which is radiating, and we are talking about the desired signal, the subscriber is at a distance of 1000 meters from the base station. Typical base stations can have a radius of 5 kilometers, though today because of higher capacity requirements the cell sizes are much smaller. Suppose the subscriber is located at a distance of a kilometer from the base station, whereas another mobile which is using an adjacent channel is unfortunately at a distance of only 100 meters from the base station. Let us say that they are in South Delhi, where the path loss exponent is close to 3. Prior to filtering, the signal to interference ratio can be calculated as S over I is equal to d1 over d2 raised to the power minus n is nothing but 10 to the power minus 3. In terms of dB, it is minus 30 dB. So, my desired signal is actually drowned out. The near far effect, something has to be done about it. In fact, what should be the sharpness of the filter, how fast should the filter roll-off factor be, these should be determined based on what is the signal to interference ratio provided, right. And based on the roll-off factor of the filter, we can find out what is the minimum channel separation in terms of frequency bands required, so that the signal to interference level is at a certain desired level. Yes, question?
Isn't this dependent on the power of transmission? Is it just a function of distance from the base station?
The question being asked is the signal to interference at all dependent on the power of transmission? Is the transmitted power coming into the picture? So, the answer is no. The transmitter power is the same for both the desired and the interfering mobile station. So, even for adjacent channel interference, assuming both the handsets are identical, their peak and average transmit powers are the same, and the received strength depends only on the distance between the transmitter. In general, neither co-channel interference nor adjacent channel interference can be reduced by playing with the transmitted power. So, let us come back to this example where we have found out that this signal to interference ratio is actually minus 30 dB. I can barely extract out my signal unless I have a good filter. The other method to reduce the adjacent channel interference is by smart frequency separation. That is, you have a frequency band which has sub bands to be allocated to different users called channels. Now, clearly, as and when the demand arises, you have to assign the frequency bands. But you should not start with the first band and then the next band and then the next band. In fact, you should have maximum separation. There could be several algorithms. Let us take an example. Suppose these are a set of frequency sub-bands allocated to a single cell, and my job is to allocate these frequency bands. But the objective is to ensure that the frequency separation between each channel is maximized. Now, it is early in the morning and the first user requests for a channel. So, I, as a person who is trying to assign different channel, gives, say, the first channel. It could be any one of the channel, and I have picked up the first channel. Clearly, when the second request comes, I should not give the second band here, neither the third band. In fact, I should give the most farthest apart. So, I will give the second user the second band, which is the farthest apart. Clearly, the demand is increasing, and so a third user requests for a channel, and I give a channel which is almost equally spaced. I could have given this channel as well, but for the sake of an example, I have assigned it this channel. And then the next user requests a channel, I have to put it which is maximally apart, and so on and so forth. So, you get the picture as to how the channel assignments have to be done in order to maximize the frequency separation. So, the next user requests, and clearly you see the pattern. I am trying to fill the gaps in such a manner that the frequency separation is maintained. Now, at this stage, I have been able to assign 1, 2, 3, 4, 5, 6, 7, 8, 9 channels, and I have stopped at this location because the 10th user, when requests a channel, has to be put adjacent to some other channel. I have run out of gaps. Please note, initially there were 22 slots to fill, but I have run out of slots by the time I have reached 9 users. I have not done a good job. In fact, had I put alternate frequency separation bands, I could have handled 11 channels and still had the same level of adjacent channel interference. Please remember, even though these channels are separated, there still will be adjacent channel interference. It depends on how sharp your filter is. Please remember, your adjacent channel strength could be 30 dB higher, 1000 times higher than your desired signal. So, even though your frequency bandpass filter is trying to cut off the filters, a fair amount of power can actually leak in. So, these red guard bands do exist, but they barely solve much of the problem. So, when the 10th user requests, I put in the 10th user here, and is the first guy who gets actually a channel adjacent to one of the existing channels, but I had no choice. I cannot deny the service. And then the next request comes, I fill it more, and so on and so forth. So, as a requests come in, I keep on assigning channels, and I am filling it up. So, the moment I fill up, so all these people are having a hard time, right? And here I have not differentiated between a voice channel and a control channel. The channel adjacent channel interference as well as the co-channel interference can cause not only crosstalk or background noise in voice channels, it can cause a call to drop or a call to be blocked. So, I am filling up more and more, I have 2 more slots available, and finally the last slot, and I cannot give service to any more people, and the service that I am giving may not be of the best quality also. All right. If another person requests, I can either borrow a voice channel as we have seen earlier, or we can say, sorry, all lines are busy, please call after some time. Fine. So, at this point, let us conclude today's talk by summarizing what we have learned today. We have looked at the different kinds of interferences, namely the co-channel and the adjacent channel interference. We looked at the co-channel interference in greater detail because it is of big concern. We looked at how to calculate the co-channel interference values. Specifically, we looked at the average case as well as the worst case analysis. We learnt that these 2 cases have a direct relationship with the path loss exponent being used, and then we looked at the adjacent channel interference. At this point, let us conclude our talk, and the next time we will talk about power control to reduce interference. Thank you.